February the 4th, 2022. Welcome to the 12th lecture in Lattice Boltzmann methods. Today is an advanced topic, the Cumulant LBM methods. So there's not too many things on the agenda, but they are pretty important. So okay, we talk about the binomial transform that allows us to translate between raw moments and central moments. Then we will discuss the breakdown of the Galilean invariants if we use MRT with raw moments, and then we introduce the cumulants. Okay, so remembering last lecture, if you didn't hear it, go back and see it. So in lecture 11, we learned that in order to eliminate the interdependence of this moment M211 and M011, where M211 depends on M011, but not the other way around. When we want to remove this, we actually have to relax a different moment, which we identify as a weighted orthogonal moment. So this obviously implies the question whether this was the only moment that produced such a problem, or whether there are other interdependencies on other moments. And another question that we will answer first is what actually is with the frame of reference in which we take these moments. So we have seen that the classical MRT, which is the one from Lallement and Lou, uses raw moments. They make them orthogonal, but still it's raw moments. Because we call them raw moments, because they are in the Eulerian frame. And there's another method which we did not explicitly introduce, but that uses central moments. Central moments, MRT. Uses, of course, central moments, obviously. And this is the Lagrangian frame. Okay, what does this mean? Let's first look at raw. Raw moments. They are Eulerian, and we have central Lagrange. Okay, one funny thing is that Euler is of course a German and Lagrange is a French. And when Lattice Boltzmann was introduced, or derived in different ways, the Frenchmen used the Eulerian frame and the Germans used the Lagrangian frame. So in that sense, there's a good exchange here with European nations. Yeah, so the the Ra moments, you find M, A, B, C. They look like this, and we have seen them many times. This is the sum over I, J, and K into I, A by the power of A, J by the power of B, and K by the power of C. F, I, J, K. So this is the Ra moment, and the central moment then is, we write them as K, A, B, C for historical reasons, is of course the same sum. However, instead of I, J, and K, we have here I minus U, this is the x velocity divided by the lattice velocity C to the power of A, J minus V, which is the y velocity divided by C by the power of B, and K minus W, which is the z velocity divided by C. And, oh, I just recognized I have to write this in a capital C. Yeah, so the lattice velocity will be a capital C here, and I have a small c up here. So these two c's are not the same. It's just that I run out of letters, unfortunately. Okay. So this is the difference between central and Ra and central moments. So the central moments make this this distribution here symmetric by setting that K 1, 0, 0 and K 0, 1, 0 and K 0, 0, 1. Yeah, they are all, let's get rid of this comma, they are all by definition 0. Yeah, so we define the velocity in such a way that these first order moments disappear. Okay, so between Ra and central moments, we can transform by using the so-called binomial transform, so that we see that if we have the one, we can calculate the other one. Binomial transform between frames of reference. So these are the two, I mean, there's of course infinitely many different frames of reference. However, these are the two that make sense. Yeah, so the Eulerian frame is the frame of the lattice, so the frame in which we solve our equation, and the central, the Lagrangian frame, is the frame of the fluid. Yeah, so these are the two frames that make sense. And of course, you can define any other frame of reference too, but then they don't have an they may not have a justification for using that particular frame. So the central moments K, A, B, C, they can now be computed from A is equal to 0, from 0 to A, sum over J from 0 to B, and from K from 0 to C. And here comes the binomial A over I, B over J, and C over K. And this into minus 1 by the power of A minus I plus B minus J plus C minus K. Yeah, okay, again, this, yeah. Yes, and this multiplied by the raw moments Mij, M100, which of course is the velocity, M100 divided by M000. This is the velocity by the power of A minus I, M010, M000 by the power of B minus J, and M001 divided by M000 by the power of C minus K. So this is the way you transform between raw moments and central moments. And what you see here is that the central moments only depend on raw moments up to the same order, and the order is always the sum of A, B, C, up to the same order. So there is, yes. Okay, so in the thing here, this is not a vector, just for a reminder, the binomial. This is A over I is equal to A factorial divided by I factorial A minus I factorial. So this is what we have in this equation. Okay, so this is this transformation, and now we look at it first in 2 dimensions. Yeah, so what does it mean? So if we have k to 0, and we put this into this equation, and then just giving the results, k to 0 is m to 0 minus m10 square divided by m00, which we can also write in a more compact fashion as m20 minus u square rho. And we have, for example, k11. This is equal to m11 minus u, v, and rho. And now if we remind ourselves that m20 equilibrium is equal to u square plus theta rho, then this means that k20 equilibrium is just equal to theta rho, which makes sense. So the central moments, their equilibrium is of course no longer supposed to depend on the velocity, yeah, because we put the velocity already in the definition of the moment. So in the frame, in the frame in which we take the central moments, because it's the frame of the fluid, the velocity must be 0. Yeah, so the equilibrium for central moments, so equilibrium for central moments, is not a function of velocity. So the okay, now we see that there's two different ways. Okay, there are infinitely many ways actually to frame this equation, to give, we can do this in any frame of reference. And the question is now whether this makes any difference, because it should not, yeah? So the frame of reference should not influence the behavior of the method, because the frame of reference is arbitrary. Okay, so you can assume that it will, of course, influence the method. However, it should influence it only at high order, yeah. So that asymptotically to leading order, it should not influence them. Okay, in order to investigate this, we look at the relaxation of raw moments expressed in central moments. So we use the method in one frame of reference and look what it does in another frame of reference. Yeah, so relaxation of the raw moments. So this is the Eulerian frame of reference. And we look on what this does in the Lagrangian frame of reference. And what we hope is that it doesn't matter, that they do both the same. That would be correct. Okay. Let's start with the moment m20. So m20 after collision is m20, and now we make our life simple and say, okay, there's a specific relaxation rate attached to this moment, which we can also do, attach one to the sum of them, but we now assume that this is just the relaxation rate omega 20, and this goes into m20 equilibrium minus m20. So this is how we usually would relax such a moment. Okay, and now we can express all of these guys in terms of central moments. So we start with the left-hand side where we have the post-collision state, and here we have the post-collision state of the central moment plus u square u square rho. Yeah, so this is because u square doesn't change in the collision and rho doesn't change in the collision. They are pre and post collision is the same. So on the left hand side, and what did I say? So this is the left hand side, and now we come to the right hand side. So we have k, the pre-collision k20 plus u square rho, and we immediately see that these two guys disappear, plus omega 20, and here we have k20 equilibrium plus u square rho minus k20 minus u square rho. And okay, we see again that this disappears and this disappears, and we end up with k20 asterisk is equal to k20 plus omega 20 into k20 equilibrium minus k20. And this is, of course, something that makes us very happy because this is what we expected. Yeah, so whether we whether we relax this moment or this moment, the behavior is exactly the same. Okay, so we observe that relaxation in Eulerian, in the Euler frame and the Lagrange frame, give the same results for the second order moments. And the good thing is that, okay, so the same, we don't show this, but the same would be also for happen for k to k02 and k11. And this is a good thing because these are the moments which we care about most. Yeah, we care most about the relaxation of the second order moments. And third order moments and up, these are just ghost moments. Yeah. But if we want to look into the details, we of course also have to see what happens later. So third moments, or let's say 1/3 moment. Okay, let's take 1/3 moment, k21. K21 is, if we plug it into the transformation, it's is m21 minus 2u m11 minus v m20 plus 2u square v rho. So I hope this is correct. Okay, so now this is this transformation between mk21 and m21, and we immediately notice that there is a difference between what we had in the second order moments and the third order moments. So in the second order moments, we only had to use some velocity part, which was a conserved part. And here we also have a conserved part. But in addition to this, we also have a not conserved part. So let us see whether this makes any difference. Yeah. So this requires a bit of writing. So first of all, there are these non-conserved moments, which we have to write down. This is m11. This can also be written as k11 plus uv rho, and m20 is k20 plus u square rho. So this is the transformation in the other way around. And this means that if we plug this into the above, we can say that m21 is k21 plus 2u k11 plus v k20 plus u square v rho. So, okay, I'm writing this from my sheets. I hope that this is correct. Okay, so this is the transformation between the third order moment in the third order raw moment and the central moments. And now the thing that we observe is that this depends on 3 different moments, of which all are not conserved. So all of them have to relax. So let's look at the relaxation in the Euler frame. So we have m to 1 is equal to m to 1 after collision is equal to m to 1 before collision plus omega to 1, say, m to 1 equilibrium minus m to 1 before collision. So now we can replace all these guys with their equivalent central moments. So the equivalent central moments on the left-hand side, k, the post-collision, k21 asterisk plus 2u. Here again, k11 after collision plus vk20 after collision plus u square v rho. And now we come to the right-hand side where we start with the pre-collision states. This is k21 plus 2u k11 pre-collision plus v k20 plus u square v and rho. Okay, we are not done with the right-hand side. We also have to have the collision operator. This is omega to 1, and now everything comes for the equilibrium state. This is k to 1 equilibrium plus 2u k11 equilibrium plus vk20 equilibrium plus u square v rho. So this was the equilibrium part. Comes the pre-collision part, k minus k21 minus 2u k11 minus vk20 minus u square v rho. Okay, so what we see again is that this conserved part can always be eliminated from here and also from here. Now we also have to use the collision of the moments here. And the good thing is that we already derived that the second order moments, for the second order moments, it does not matter whether we relax central or raw moments. So I write the collision here in central moments because this is the same as doing it in raw moments. So this is what we 20, and we had k11. This is k11 plus omega 11 k11 equilibrium minus k11 pre-collision. Okay, so now we have to plug all of this again into the above equation. So we have k21 after collision plus u2u omega 11 k11 equilibrium. So I've already eliminated the pre-collision part here because I do not want to write too much. I'm just giving the result. So you are very, very welcome to go through the entire calculation yourself, but we have to go on. So I just present what results from this. So we have k21 plus omega 21 k21 equilibrium minus k21 plus 2u omega 21 k11 equilibrium minus k21 1, 1 plus V omega 2, 1 K K2, 1 equilibrium minus K2, what did I say? K0, K2, 0 minus K equilibrium minus K2, 0. Okay, so now this can, if we put everything on the right-hand side, we can rewrite this as K2, 1 after collision is equal to K2, 1 before collision plus omega 2, 1 K2, 1 equilibrium minus K2, 1. Okay, so this is what we like to have, and in addition we have plus U omega 2, 1 minus omega 1, 1 into K1, 1 equilibrium minus K1, 1 plus V omega 2, 1 minus omega 2, 0 into K2, 0 equilibrium minus K2, 0. Okay, so I have to say that this is the simplest moment for which this happens. So if we look at the first order moment, the calculation would take the entire 2 hours. So, but what we already see is that we have this part here, which is, so to speak, the happy part, because this is the Lagrangian frame. So if we relax everything in the Lagrangian frame, we would do exactly this. So, however, we relax in the Eulerian frame, and because we relax in the Eulerian frame, we have, in addition, we have these guys. These guys here. And they depend on the velocity. Yeah, so the collision in the Lagrangian frame, the collision is not allowed to depend on the velocity. Yeah, so this here is a violation of Galilean invariance. It's violating the Galilean invariance because it depends on the velocity. So there's another thing where it depends on. So you see that supposed we would have the same relaxation rate for the third order moments and the second order moments, yeah, then this thing here would disappear. So what we do in BGK would make these things here disappear. But since we want to use MRT, we want to use different rates for different moments, we are actually violating Galilean invariance. So I hope that everybody knows the concept of Galilean invariance, just in case you have problems with this. Again, what is Galilean invariance? Galilean invariance is the statement that each law of nature must be invariant under the under the inertial frame in which it is stated. So this is not completely physically correct. The reality is that it should be Lorentz invariant, but this is a good assumption if we are far away from the speed of sound. Yeah, so no matter in which frame of reference we state our problem, it should always give the same results, and we just observe that this is not the case. So it is not the case for the third order moments. They are not Galilean invariants. Unless the different relaxation rates are the same. So, and this would of course imply we should use BGK. However, this is not an advertisement for BGK. This just says that there's something wrong in the way we relax these moments. This doesn't mean that we have to use BGK. So, and now, there is an important point that could be made, namely that we use a lattice for discretization, and if we use a lattice for discretization, we of course always have a preferred frame of reference. So we cannot assume a priori that our system will be Galilean invariant, right? However, the important thing is that in our derivation that we just used, the discretization was not assumed. Yeah, so what we just derived would be the same whether we discretize it in the way we do it or whether we do not discretize it. So the discretization would of course cause additional problems to Galilean invariance, but in that particular case that we looked at, we did not assume, so the discretization of the velocity space was not assumed here. So what we observe here is not a discretization artifact. And it can also not be repaired by using a better discretization, because it does not arise from the discretization. Okay, so where does this leave us? This leaves us at the observation that there are two fundamental problems with BGK. With MRT. And these are problems besides discretization errors. So discretization errors come on top of this, but they are not meant by this. So besides discretization errors. So the first problem that we have is with the ghosts. The ghosts are not independent, even if orthogonalization is used. And the other thing is that the ghosts are not Galilean invariants. So these are the two problems with this approach of MRT, conceptual problems. So interestingly, both problems disappear if all relaxation rates are the same. So this means for BGK. However, as I said, this is not an advertisement for BGK. So BGK has its own set of problems. So this leads us now to, we have half time, this leads us now to the question or the recognition that maybe, just maybe, moments are not the best basis for MRT, and we could use a different set of variables. And this different set of variables, this is called cumulants, and this is now where we come to the second half of this lecture, the Cumulon methods. So, okay, what do we need to do? We need to find a set of independent variables my handwriting is not good today. That can relax with different rates without influencing each other. And we need variables, so this of course need to be the same variables. which are not variables which are not independent. So if variables depend on each other, they cannot decay independently. Okay, so what I mean with this is, so if there is something that changes if within a particular frame, right? So like or time scale. So for example, there is COVID infections and there is people with COVID in the hospital. Yeah, so then you should usually assume that when one number goes up, the other number goes up, and when one number goes down, the other number goes down. So now we observe that there's an uncoupling between these two things, because we also have vaccination. But suppose these two things would be if they depend on each other, yeah. If there's always a fraction of people who have the infection in hospital, then we will see that both quantities grow and shrink on the same time scale. So they cannot have different relaxation numbers. Otherwise, they would not be proportional to each other. So I recognize I made a bit of a bad example, because just currently we have now different rates in. We used to have higher numbers of people in hospital for the same number of people who were infected, but the reason why this has decoupled is because we now have a different virus. Before we had the Delta virus, and now we had the Omicron virus. Yeah. So if we still had the Delta virus, and if we still had no vaccination, then we would observe that the number of people in hospital are still proportional to the number of people that are infected. Okay, so now, so we are talking a lot about that variables are coupled, and some variables are coupled and some variables are not coupled. So we have to specify what it means statistically. What does it mean for statistical variables? To be independent. Okay. So random variables are independent if knowledge of the one does not give knowledge on the other. So knowledge on the state of, say, X implies no knowledge on the state of Y. So suppose I throw two dices and I tell you what is that the first dice got 3, and you should tell me from this information what gave the second dice. And of course you don't know, because these two dices are independent. Yeah. However, if we again look at the COVID numbers, if I tell you, so today we had so and so many infections, then you may have a guess. Then if the number of infections goes up, then probably the number of people in hospital also goes up. So they are not independent. Okay, in regard of this independence, this also means that, things should not, as things should not depend on each other, we observe in MRT that immediately that there is a problem, namely, we observe that the equilibrium of the non-conserved moments they are usually functions of conserved moments. And this is already strange. Yeah, because if the equilibrium of a non-conserved moment is a function of the conserved moment, and the equilibrium is always the strongest part of a moment, so it's always at the lowest order. So this means that information on the, or say knowledge on M, say M10 would already imply some knowledge on, say, M11 or others, other higher order moments. So, and this means they are not independent, obviously. Okay, so this is a very important caveat that you have to take in consider in mind. So if the moments in the MRT method were really independent of each other, as is the promise by making them orthogonal, then it should not be possible that their equilibrium depends on each other. Yeah. So once you see that the equilibrium of the second and the third and maybe the fourth order moment in MRT is a function of the velocity, which is the first order moment. This simply means they are not independent of each other, because there is an influence of the second and the third order moments on the first order moment. And by definition, this means they are not independent. Yeah. So this can't be. So there is something fundamentally wrong in this approach. Now let us recall how we actually come to these moments. Yeah, so we come to the moment from the so-called moment generating function. So the moment generating function that we call capital F is in a frequency space, the integral from -infinity to infinity, f xc, or also the distribution function in the velocity space by the power of e xc small xc, which is the velocity, large xc, which is the Fourier transform or the Laplace transform of the velocity, integrate over the velocity space. and this is the moment generating function, which of course is a function of all the moments mi. So this is the probability distribution in frequency space and this is basically a Laplace transform up to the sign. Yeah, so for whatever reason in statistics we do the Laplace transform in the other way around. So in the Laplace transform we would have a minus in the exponent, and here we have a plus in the exponent. So but this doesn't matter, it just means that we prefer to use positive numbers for the moments. Otherwise all the moments would be negative by default, yeah, which is somehow strange. So, okay, now this gives us the moments, but the moments there is no control on their independence, yeah? So the question is how to make variables independent, and in statistics there is random variables are independent if their distributions factor. So we require that f mi, so this function should be expressed as a product, so a factorization of an fi ci. I should probably write this, okay, should write this in a little bit different format. So this f m1 mi and so on, yeah. This should be a product of distributions that are, so to speak, univariant, so that all of them are attached to only one variable. So basically it means that that we can express a distribution of many variables as a product of distributions of single variables if these single variables are independent. Okay, so this is not a proof, but this is where things are where the Cumulant method is basically coming from. So if ci, so there's a variable ci and cj, if they are independent, which we are looking for, then their joint probability distribution factors. Okay, I have to admit that this definition of independence in of moments or cumulants or any quantities, this is always a little bit fuzzy, yeah, and I'm still looking for a very good explanation about this, but as an excuse, the guys from MRT also never really explained why they try to obtain this by making things orthogonal, yeah. So if we do not completely understand it, then just take it as an empirical approach. So we factorize this distribution function. Again, look at what are moments. Moments is MABC. They are derived from the moment generating function by taking derivatives in the different variables, where again this velocity frequency, which we had in one of the earliest lectures, is here the vector of the frequencies in the different directions. So we call this epsilon in the epsilon direction and zeta in the z direction. So this is now this moment generating function, and we do all of this at frequency equal to 0. Yeah, and this gives us the other way around, if you will, is the sum of A, B, and C from 0 to infinity. And here we have xi by the power of A, epsilon by the power of B, and zeta by the power of C divided by A factorial, B factorial, C factorial, and this goes into M, A, B, C. So from the moments we can come to the moment generating function. So the moments are the parameters of the series expansion of the moment generating function, obviously. So, but the moments, they are not independent variables. We are looking for independent variables. So now for independent variables, or say observable quantities. So in German we can just say observables, but I think in English we have to say observable quantities. So that we call CI. So we defined that, okay, we have the same moment generating function, and this should be expressed as a product of I from 0 to infinity, Fi, Ci. Yeah, so we can split these guys up. Okay, so if this is a product, what we can do is we can take the logarithm of f from the f of xi, and this will of course be equal to the sum from 0 to infinity of the logarithm of fi from f of ci. Okay, so then we have the thing in the same form. Both here we have a sum and here we have a sum. Yeah, and now we can define this as the so-called cumulant generating function. The cumulant generating function, which we simply define as the logarithm of the moment generating function. And this now looks exactly the same. It's A, B, C from 0 to infinity, xi A epsilon by the power of B and zeta by the power of C, by A factorial, B factorial, C factorial. And here comes the cumulants, C, A, B, C. Which equivalently means we have C, A, B, C is equal to the derivative, the 8th derivative in Xi, the bth derivative in upsilon, and derivative, the z derivative in Xi of the logarithm of f of vector Xi at the position, close the brackets, at the position Xi equal to 0. So now what we are doing is we still do MRT, however, we don't do it with moments, but we use it with cumulants. Instead of moments. So that's all what we then observe, that, and without considering discretization artifacts, which of course we still have, but otherwise this is Galilean invariant. So it does not depend on the frame of reference. And we've eliminated the dependency of the observable quantities. At least we claim. So we have not proven this, but we claim this. Okay, let's we look at some examples in a minute. Okay, so suppose we are happy with this conceptually, then we come to the problem, how do we actually compute cumulants? And this is the biggest problem. So the idea to use cumulants in Lattice Boltzmann is not particularly new. However, the big difficulty was to actually, how do we compute cumulants? Because this is not necessarily easy. Yeah, so we see that the C001 is supposed to be the derivative in z direction of the logarithm of f for Xi equal to 0, and this can also be written, so we have to use the chain rule in this, so we get to 1 over f d z f Xi equal to 0. And so this guy here, this is of course just the zero order, the first order moment, and this here is the zero order moment. So what we get out is m001 divided by m000, which of course is the velocity in z direction. So this is w. Yeah. So if we look at C002, what will happen? We have dz. So dz, the second derivative here of the logarithm of f at position Xi equal to 0. And if we do this, we'll end up with the first derivative, dZf. There's something wrong. So dz square f divided by f square. No, wait. Sorry. df. Right. So this is correct. So dz f square divided by f square plus dz. So the second derivative of f divided by f, and this gives us m002 divided by m000 minus v squared. So in this way, using the chain rule, we can actually compute the cumulants from moments. So this is the easiest way. Now, yeah, what we observe here is that this gives us exactly the velocity. If we look, give another look on these on the second order things. So, in particular, the trace of the second order moments, which is of course the sum of these three guys here. This is called the trace of the second order moments, because it's the diagonal of the matrix. If you put it in matrix form, second order moments, that would be the sum of the diagonal. And if we compute this and plug in the moments, what we observe is that this just gives theta. And theta, as a reminder, is the temperature. So now we have something very, very interesting, yeah. Namely, we observe that the first cumulants, they are velocity. So the first moments, they have been a momentum, yeah. So this is an extensive quantity, but the first cumulants is an intensive quantity. It's a velocity. And what we observe with the trace of second order moments, second order cumulants, this is the temperature. Okay, so the funniest thing is we have something very, very abstract from a mathematical point of view. So we said, okay, we are looking for independent variables, so we take a factorization of this moment generating function in order to derive these independent variables. And what comes out of this is things from nature which we know very well, yeah. So what drops out is the velocity and the temperature, yeah. So it's not momentum and kinetic energy or strange things, but they're really things that we can see and feel. Velocity and temperature comes out. So, and now the question is, what happens to the other guys? Well, the other guys disappear. So the equilibrium of all other cumulants is 0. Okay, so we started up with something extremely abstract, and we ended with something pretty intuitive, yeah, velocity and temperature, and basically nothing else. Okay, let us have a look at the relationship between cumulants and central moments. Okay, so we look at the change of the frame of reference according to the translational rule that we have for the Fourier and Laplace transform. So I really hope that your mathematics professor teaches you Laplace and Fourier transform, because we cannot go into too much detail, but if we have something in an Euler frame and we put this in the different frame, Lagrange, so what happens is that we get a new distribution function in the Lagrangian frame times an E plus U times zeta, xi. So this is what happens if we translate the frame of reference in a Fourier or Laplace transform. However, where we have to keep in mind, so if you look in the book, will be different because our transformation has a different sign convention. So unfortunately, we have a different sign convention from the usual Laplace transformation. So instead of having a minus here, we have a plus here, but this is the only difference. So this means if we do this transformation, say CABC equal to these derivatives, I'm not good in writing these Greek letters. So we have the logarithm of now f e u xi, and what you see, xi goes to 0. We can simply rewrite this because there's this logarithm. This is not a gamma. I always want to write a gamma. This is an upsilon, upsilon b, zeta c. So we use the law of the logarithm to write that this is u dot xi plus the logarithm of our f in the new frame for xi going to 0. So now what we observe, if we take this derivative, we see that only the first moment, the first cumulant will depend on u, and all the other cumulants will not depend anymore on u. Yeah? So we put all the dependency on the velocity or the frame of reference in the first order cumulants, which of course we want to have. Yeah. So the velocity, the frame of reference, should only influence the velocity and nothing else. So all but the first order cumulants are frame independent. So this is very important. This makes the entire thing Galilean invariant. Now, from a practical point of view, it's easiest to write cumulants in terms of raw central moments. Or this is more efficient than to write it in raw moments. So the reason for this is as follows. So writing cumulants in terms of central moments is more efficient than in raw moments. So this is in particular the case for high order cumulants, but I'm showing it only for the second order cumulants, or for brief discussion here. So the cumulant C002 is M002 divided by M000 minus M001 squared divided by M000 square. And because cumulants are frame indifferent, they can be stated in the other frame too, looking like this, minus K001 square divided by K000. So the important thing is we can always write, we can use exactly the same equation for central moments and for raw moments, because cumulants do not care whether they are taken in central or in raw moments. So then what is the difference? The difference is, by definition, of the central moments, K001 is equal to K010 is equal to K001 is equal to 0. So all occurrences of first order central moments in these equations will simply drop out. And this makes calculating cumulants from central moments so much more efficient than from raw moments, because in particular at high order moments, there are very, very many terms in these equations that depend on the first order moments. Okay, so this is something that we come to in the next lecture, how we actually efficiently compute cumulants. For now, we look at one last example, whether the cumulants actually solved our problem. So we put cumulants to the test. And for this, we recall the problem we started on today. So when I started this lecture, I was alone, so I'm happy that some people showed up. So when I explained this, I was still alone. And maybe everybody else looks it in YouTube, I don't know. So let's recall the problems with the moment M211. The problem that is observed in actual simulations, that depending on what sort of orthogonality you are using, you either have an extreme overdamping of this moment, or you get instability. So whatever you do, you get some problems, but we already had one solution for this. Which was a kind of ad hoc solution. So unless the moment is changed to, so we had N211, which we say is equal to M211 minus theta M011. So if we relax this guy, then this problem that either the simulation goes unstable or we get an extreme overdamping, then this can be avoided. Now, what does the cumulant say about this? So what about the cumulant C211. So what happens if we relax this guy? Okay, let's look what it actually is. C211, so if we expand this in terms of central moments, we get K211 divided by rho minus K200, K011 plus, this is a 1, plus 2 K110, K101, and we've already eliminated all parts that are related to the first order central moments because we know that they are 0. So, and this is not rho by the power of 1, but rho by the power of 2. Okay, so the problem we observed. So of course it's not completely the same whether we use this moment or this cumulant, but we observed this problem at a particular order in the asymptotic analysis, and this was second order. So let us look at this cumulant to the second order only. So if this is the second order, then we have this here to the second order divided by rho to the zero order minus K200. We could have this to the 0 order and this to the second order, which gives in product, this gives the second order, or we could have K200, K to the second order K011 to the 0 order. What we could still have in theory is that we have K200 first order times K011 first order. But however, since these are even moments, they only have even order. So that we do not have to consider K2001. So this doesn't exist. Yeah, so then we have plus 2 K11 0 to the second order times K101 to the 0 order plus K110 to the 0 order times K101 to the second order, and this divided by rho to the 0 order. Now to the 0 order, these guys here would be the same as the equilibrium to 0 order, and the equilibrium to 0 order is 0 for the central moments, and for K200, which we've already seen, to 0 order, this is theta times rho 0, and if we plug this into the cumulant, what we're left with is K to the second order, C to the second order is K101 to the 0 order. Sorry, what did I write? Sorry. K211 to the second order minus theta K011 to the second order, which is exactly what we found to solve our problem. So the cumulants simply takes care about this problem automatically. So they remove this problem And now the hope obviously is that we do not need to look for, for more problems of this kind in order to do any more ad hoc solutions. in the MRT framework, but we can simply use the cumulants and they solve these problems for us automatically. Okay, so we come to the last sentence of today. We are done in a minute. So we have free choice now of relaxation rates for our ghost moments because we have eliminated this problem, and this requires that we use cumulants. And as a teaser, and the very, very last thing now today is there is such a picture where we compare BGK, MRT, and here the cumulants. If we do simulations on the same resolution, we can resolve much more. So this is always the same resolution, but we can resolve much more detail. Actually, if we go from BGK to MRT, we can resolve more detail. But if we go from MRT to cumulant MRT, we can simulate much more detail with the same resolution still. So, but we are running now out of time. Thank you for attending, and we'll see you each other next week. Stay tuned.